We're going to start a unit now on light. We've started with waves and we've talked about some of the basic characteristics, but we want to focus in on really what light is and how it interacts. So, light is a transverse wave, and it is produced by the motion of electrically charged particles. And we know that a transverse wave means that the direction of the wave and the motion of the particles is going to be perpendicular to each other. And oscillating electric and magnetic fields are at right angles to each other, and this does not require a medium. And the speed of light, the variable given for it is going to be c, and it is equal to 3 times 10 to the 8th meter per second in a vacuum. And even though it does slow down in air and in other media, it's still way faster than sound. Here is a picture of the spectrum of electromagnetic radiation, and you can see that the part we actually live in and focus on and try to explain is really a very, very small section of that. The visible light, broken up into the Roy G. Biv that you have learned before, is all right there in that one little section of visible light, but there's lots of other kinds of light in the electromagnetic spectrum. This just gives you kind of an indication about how the different types of radiation of electromagnetic radiation are related. And you can see that very large waves are down at the radio waves end, roughly the size of buildings. This is why the mountains and city streets and all that does interfere with radio transmission, but it can go over and smaller objects very, very easily. And all the way to gamma rays, which are going to be the very smallest and the most energetic because the wavelengths are the shortest. Radio waves are the long wavelengths with very short frequencies, and they have the lowest energy of all the types of electromagnetic radiation. And we use them in very common day ways like radio, television, cordless phones, radio towers you see around as you drive along the highways through the countryside. Sound waves can be changed into electrical currents, and so that's what you do when you pick it up in a microphone, or these microphones are the best ways to do that. The currents then vary their amplitude and frequency and transmit the waves, and then on the other end they're turned back into sound. If you've ever watched a speaker, it vibrates and it's going to send out those pulses, those longitudinal waves that we would hear in our ears as sound. Microwaves are slightly higher frequency and have more energy than radio waves, and we use those for communications like our cell phones. We also, as you know, use them for microwaves for radar. Okay, microwaves transfer the energy to the water molecules. The part that they can really affect very, very easily is the water molecules. As the water molecules gain kinetic energy, they will increase in temperature. We learned that in chemistry. And then as those will vibrate, they will heat the substance up. Glass, paper, and plastics allow microwaves to pass right through them, so they don't gain much of the energy, and so most of the energy is going into the food. Infrared, slightly higher frequency and more energy than microwaves, lower frequency and longer wavelengths than visible light. And this is the kind that we use to keep our food warm in buffet lines. We also have experienced it inside of cars. You know that the infrared can get in. Radiation can get in and it's turned to infrared, which is then trapped by the glass. Infrared is used in night vision goggles, home security systems, heat lamps, and drying devices. And now they do a lot of research with pinpointing tumors and all, and they can be used to diagnose these tumors because they're warmer. One of the neat things too is now that they can, with nanotechnology, they can target them, actually put drugs on to the proteins of the tumors, and then they attack it with even greater heat. which causes a disruption, and then you can actually destroy the tumor without destroying the tissue around it. Some really neat stuff going on there. Visible radiation is the only part we can see, hence the visible part. And visible radiation allows us to see. It can help stimulate, of course, photosynthesis, and it even helps with chemical decomposition. It's a source of energy. Ultraviolet, or UV radiation, has a higher frequency and more energy than visible light. It can go through more objects, as you know, that it can go through our skin and give sunburns and all. So the greater penetrating power than normal light. It's good in that it helps you produce vitamin D. Get too much, of course, that's bad with skin cancer. But you do, a lot of people that work inside buildings and don't get out very much, they actually need to take vitamin D supplements because they don't get that exposure. So that's kind of a bad thing if you live up north during the winter months. They have a hard time producing enough, and that's one of the reasons that there's vitamin D in milk, is you've got to get it somewhere. So that's one thing that they can put it in. Ozone blocks most of the UV rays. This is why they're worried about ozone levels if they're too high, because that does offer some protection to us. But we are in a pretty good place now. I think they've done a lot of things to protect our environment. Sunscreen is made to absorb the UV rays before it can actually penetrate the skin, and that's how they hope to prevent cancer. We use UV light to sterilize our goggles here at this school. You can use it in a lot of hospitals. They use it to kill microorganisms so that they can really get them clean. Kills healthy cells if overexposed, and they also can cause mutations in some cells. X-rays, shorter wavelengths with greater frequency, and they have a lot of energy, and they really do penetrate, which is good because we use them to see through our soft tissue and to see the more dense things in our body, which of course are our bones. They're used to take pictures of bones and teeth because they absorb the radiation as it passes through the other softer tissues, and they do use X-rays in some cancer treatments because it is very disruptive. Gamma radiation is what we have to worry about with the astronauts in the space station. It's the highest frequency and energy level. It's emitted from radioactive atoms and comes from space. It can be very, very destructive. Lead lining can help stop a lot of it, and they even do use it for treating cancers, but it really will kill all cells instead of just the unhealthy ones. One of the big debates is whether light is a wave or a particle, and actually it is a little of both. And so it's called the dual nature of light, and it depends on what part of light you're studying. If you want to study it as a particle, a photon, or if you want to study it as a wave. We've got lots of proof that it acts as both. And so that's one of the things that we'll be talking a little bit about as we go on through this chapter. For calculations, we're going to follow the wave properties. So this is a formula that we used in the last unit. So the speed of light, which we called velocity before, is equal to the frequency times the wavelength. And as long as we can remember the speed of light, 3 times 10 to the 8th, and we are given one other part of that equation, we can solve for the unknown. Doppler shift with light. This is one of the things we use a lot in astronomy. What happens is, as light is traveling away from us or towards us, it will appear to change in its frequency. And so if an object is moving away from us, the wavelengths are coming at longer and longer intervals, so the frequency is going to be stretched out, and because of that it's going to appear more red, and so it's shifted towards the red, so we know it's moving away from us. If a star is coming towards us, it is catching up with the pulses, the light that is coming out from it, and so shortening it, and then it goes blue. And if something is spinning, one like a galaxy or a large planet, then we can actually see a difference in the light from each of the sides of the spinning object, and so we can even tell which way it's spinning. And that's one of the big tools that we use and they've used in the past to show that the universe is expanding. Brightness is how we perceive light, and it's proportional to the actual brightness of the source, and it's inversely proportional to the square of the distance. And we've got a lab that we'll do on that. But light, as you get farther and farther away, the light will decrease it as the square of the distance, so it decreases very, very rapidly. Images can be luminous or illuminated. We know that luminous is going to be creating its own light, where if something is illuminated, it's reflecting the light. And so that brings us to the idea of how do we see things, and what's the difference between real images and virtual images. And we're going to deal with that a lot as we deal with lenses and mirrors. But that's what we're going to start with our next podcast. So we're going to stop right here, and we will start again soon. See you later.